Today I'm meeting up with Albert Cohen, and he is a research scientist at Google. And we are going to discuss the HighPeak conference, which will take place in Toulouse. But we're also going to discuss compilers for machine learning, my favorite subject, you will understand. But first, good morning, Albert, good to see you. First, we're going to talk about, good morning, we're going to talk about the HighPeak conference. I think it's not your first conference in your career. What makes this special?
That's right. Thanks for the invitation. So it's a very special one indeed. So I've been working for many years on compilers for high-performance computing and embedded systems, which are the main focus of the HighPeak network. And actually have been joining HighPeak, the very first HighPeak in 2004 as a member, and got involved in many of its activities. So I was always very interested in European collaboration and projects and in these areas. And I got the opportunity invited by Koen and Koen de Bosra, who is the head of the HighPeak network, and also Per Strandstrom from Chalmers, to organize the first new model, let's say, HighPeak conference in 2012. I say new model because the HighPeak conference has been running since 2005. But in 2012, we moved to a new, let's say, publication model. We call it journal first. So our community was one of the first to pioneer this model, where we ditched the conference proceedings altogether and joined with the journal, ACM TACO, Transactions on Architectures and Code Optimization, where we decided that the papers would be evaluated through a classical journal review process, and papers accepted by a cutoff date, a certain cutoff date, would be presented and invited to be presented at the conference. Yeah. So that was a huge success. I won't go into the details. You probably know a lot about this model now. Many other communities have adopted it, but the conference has been basically increasing in size and impact very much at this occasion. So we organized it in Paris. We had about 500 plus participants. Further HighPeak conference have been going up to 700 participants. And this one in Toulouse is basically the 10th anniversary of the first HighPeak conference I organized. Okay. So it's a very special one. And we are looking for even more attendance. Industry attendance seems to be a record. Sponsors, all the presence on the industry exhibits is very impressive. So I'm very much looking forward to this.
The conference brings together a rich collection of company researchers, but also students. There will be poster sessions. This whole pressure. This whole pressure cooking of ideas and exchange of information. How do you feel this is moving forward, the next generation of computing solutions? Because that is the big issue, I think, for the HighPeak conferences.
Absolutely, and so that's a very good question, because HighPeak has been, I would not say pioneering, but at least accompanying the movement towards cyber-physical systems pushed by the European Commission and many academics and industry over the years. And the HighPeak conference has been one of the first venues for publishing cyber-physical system and embedded system, IoT type of work, Internet of Things type of work. And I would say that the biggest challenge right now I'm seeing is that all this performance we get from hardware accelerators for machine learning, embedded systems that can do online live translation, image recognition, etc. We want all these features to be much safer. So we want, and secure as well. So we want all these hardware computing capabilities to come with security guarantees, safety guarantees when they are embedded into automotives and such, and also privacy preserving guarantees. So I'm seeing a lot of research challenges in the area. It's not only engineering, it's not only policy. There are a lot of social challenges as well, but the scientific research in computer science and computer engineering is really the primary element of the solutions to these challenges. So that's where I see most of the interest right now.
I've looked at some of your materials and YouTube's in the preparation and research, but you're a next generation computing guy. And I'm an old generation computing guy. I've been learning assembler language many years ago, but But I hope in our discussion on compilers, we might find some overlap and understand, for me understanding, and for you perhaps to explain what it is. Because we're going to, one of the things you are researching with Google is machine learning compilers. What is machine learning compiler different? Why is it different from the traditional compilers?
That's a good question, and the fact you mentioned assembly language, assembly programming is a very nice way to get started, because basically after so many years, people have considered compilers a solved problem, but compilers for a very narrow part of all the problems that can be compiled. And machine learning in this respect is amazing because it's making use of hardware that's so much more diverse, heterogeneous, complex, distributed than what people typically compile for. At the level of like training large models for like natural languages, etc., we are talking about hundreds of thousands of machines with GPUs or dedicated machine learning accelerators. There is no like single assembly language for these beasts. I mean, this is super complicated, super heterogeneous. So you actually need to redefine what it means to compile for getting portable code to run on these machines, and even more challenging, portable performance, meaning that you want like a single source, a single program to run distributed on all these machines, delivering, let's say, good enough or even maybe near peak performance on these machines. That's what we call portable performance. And this has always been difficult, but it's even more difficult now given the scale of the problem. And one of the projects I've been working on before joining Google used to be called automatic parallelization, some kind of a dream where you take like sequential naive code written by maybe just someone who knows the algorithms, and you get super fast parallel distributed code out of it. So it kind of never really worked in production. It was only a research topic for so long. But one additional effect of moving into the ML in the machine learning space is that we are dedicating all our efforts on a specific domain. And domain-specific computing is a very important area of research right now.
Yeah. Now, I'm wondering, because if you look at the world of computing, you have your hardware, you have your. Today we see a complete new generation of accelerators and AI processors and etc. Coming up, and you have the software. Two forces. How are they interacting with each other? In the old days, as I say, you had the x86 architecture, or you had the RISC architecture, and that basically was the definition on how things would operate or how things would run. And the software applied to that. But I feel that what you are researching here, it is also working the other way around, that software is much more starting to define what the hardware is. How is that in your opinion? Is hardware software defining, or is it software defining hardware?
No, you're absolutely right. And actually, even the High-Peak Network has been pioneering a vision on hardware being more flexible than software. And there was one of the High-Peak vision roadmap documents that was highlighting this fact. And the fact that hardware is more flexible it reflects in exactly what you said. So when the application needs are strong enough, when there is enough money, let's say, and interest, you can actually define custom hardware for that domain, and that will be super well suited for efficient, low energy, high performance computing. And this is what happens with machine learning right now. It happened with graphical computing in the past, like 3D rendering, and maybe even in the time of x86, maybe you remember the x87 coprocessor for floating point arithmetic. That was already some kind of domain that was at the time a specific coprocessor. Now it's of course part of the mainstream. So we are expecting also maybe because of the dark silicon effect, that the processors are getting so hot that you cannot turn all the components on at one given time. So you're going to see more and more specialized units on chips and on systems. And the software has to make best use of it. But as you say, the software is actually defining which components are the relevant ones to have in these systems. And so the ML is just one instance when there is plenty of money right now allowing research and engineering to take place.
Yeah. Now, this whole field of compiler for machine learning is called MLIR. Now I feel this is a lot of stuff happening in research, in the research domain, which is understandable because these are new technologies. You cannot just you have to research them and try them and test them. But what will actually happen when all this research is actually going into the more public domain? How will how will people in 5 or 10 years recognize, okay, this is not a traditional computer anymore. This is an artificial intelligence-driven piece of hardware which works completely different. How will that, in your opinion, what is your vision on that? How will computing look like in 5 or 10 years based on this research?
In my mind, you actually asked like 3 questions. So let me start with the first.
Sorry for that.
So the first one, you mentioned MLIR.
Your compiler is overloaded now. That is parallel computing. 3 questions at a time, 3 requests.
So let me see if I can actually keep the stack in my in live. I mean, for the duration of the conversation.
Yeah, sure.
So you mentioned MLIR. So indeed, it means many things. Actually, it means multi-level intermediate representation. It's a joke. Actually, it can mean machine learning intermediate representation. Can mean many other things. But what's important there is intermediate representation, which has been the let's say the basic building block for optimizing compilers for the longest time. Like compilers, they take source languages that are human readable, make sense with the semantics that we understand, and they generate assembly code. And in the middle, lots of things are happening. That's where the intermediate representation takes place. Except that now, because we are redefining what it means to build optimizing compilers, because of these distributed heterogeneous systems, because of these domain-specific languages we are dealing with, we need a new intermediate representation. And MLIR is actually a framework for building intermediate representations, in particular for ML compilers, but not only, also used in other areas. And it's clearly, it has been a research topic for many years, let's say almost 4 years now. It has been released early 2019, but it's not research anymore. So there's still research around MLIR, but now it's really production infrastructure that's being used by many industry projects around the world, not only at Google. It's actually part of the LLVM Foundation right now, so it doesn't belong to Google anymore. And many contributors, mostly on the hardware side, but also people interested in domain-specific frameworks, invest into MLIR. So I will not go into the details of what it really looks like, but this is the reason we believe we can address all these challenges. We need infrastructure. It's not only concepts, not only research. We need actually basic software infrastructure to grow these new generation compilers. And now turning to your second question, what happens like in 5, 10 years? Before that. The second question was, what happens when we don't really program anymore, but like AI is actually driving the world of software itself. So first of all, you have to believe this is true. So obviously AI is making a very impressive foray in that space. So I won't give examples, but there are so many AI-assisted development environments right now. It's not like completely automatic still. You still need to do a bit more than writing a specification and getting code out, because if you do that, only relying on AI, you're going to get lots of bugs, misinterpretation of your specification, of your intent, etc. So it's still very premature, but it's making impressive progress. So what I see is that there is no way you're going to build systems that are programmable with AI that scale, not only for a handful of engineers with lots of resources, but that scale to massive number of programmers without the type of infrastructure we are building. It's always hidden. The compilers, when they work, you don't see them. But the reason we can actually get so much performance and getting like phones to do translation on the fly, etc., is because there is so much compilation going on underneath. So I'm not saying that we are solving the difficult problems here of getting AI to generate code and to program things automatically, but compilers are playing an absolutely essential role in bridging the gap. How I see the future in 5, 10 years, I have no clue, of course. Nobody can really predict the future, but what I would hope to see at least is much of this infrastructure get like simplified in ways that not only more users can take advantage of those infrastructures, but also more developers. Right now, you should realize that there are only maybe a few dozens engineers who really are experts in a system like the infrastructure of MLIR. And this is a problem, I think. So we are building infrastructure that's so complex, so specialized, that I don't think we are making very good uses of the resources we have in terms of like the most important resource which is people. I think we should be able to build systems that are simpler, more modular. So we made lots of progress, of course, but we should go even way beyond the state of the art. So I really hope that in 5, 10 years, we can do the same with much simpler systems, not super complex infrastructure.